Good afternoon. It's always a pleasure to be here. I heard that one gets an extra 5 minutes for every mention of the chair's name in the talk, so I decided. So in the previous hour you heard about 5 or 6 different papers by Yuval, and now you'll hear about 2 more. One is joint just with Yuval on random walks on Ramanujan graphs, and I will contrast it with work joined with Yuval, Alan Sly, and Nathaniel Berenstitsky for random walks on random graphs. Okay, so let's see how this goes. Okay, so we'll compare. The main emphasis will be on expander graphs. So the best expanders will be Ramanujan graphs. I'll emphasize. Then there are random regular graphs, which are almost as expanding as these Ramanujan graphs, and we'll also compare with the most classical random graph model, the Erdős-Renyi random graph, and see how random walks behave in all settings. This one will be connected to the previous talk because there we will see the effect of the initial state on mixing. So recall these definitions you just saw in the last hour. The mixing time is the first time where the distance to total variation of the distribution at time t to the stationary distribution is at most epsilon. Here our stationary distributions will be very simple. There'll be uniform distributions if we have a regular graph, and in general just proportional to the degrees. And the dependence on epsilon is captured by the cutoff phenomenon. So in general, mixing time, this T mix of epsilon could depend on epsilon. And to understand it, we look at, this is the graph of the distance, this distance, the distance in total variation to the stationary distribution. So this graph always decays exponentially once it goes below a half. But some cases it decays faster, and this is the case of cutoff. So we capture it by looking at this T mix epsilon, where you reach epsilon. And this, besides depending on epsilon, there's also an implicit dependence on the size of the system. And what we'd like is that the ratio of T mix epsilon and T mix epsilon prime will go to 1 as the system goes to, the size of the system goes to infinity. So that will be the cutoff phenomenon. And the simplest examples of, or I shouldn't say the simplest, the earliest examples of cutoff were in the setting of groups. So random transpositions on the permutation groups. You have n cards. Choose one card with the left hand, one card with the right hand, and transpose them. It might be the same card. And so there's an easy lower bound there of n log n over 2, because you have to essentially touch all cards before you can mix, because a random permutation just has one fixed point in expectation. But the non-trivial thing is that n log n over 2 is really gives you the mixing time, so up to, and so that's the mixing time with the right constant, so n log n over 2 with the higher order correction. Random walk on the hypercube is another example, in some case simpler. So we take the lazy random walk. We have n bits, choose a bit at random, and replace it by a fresh random bit. That's the lazy random walk on the hypercube. And again, the mixing time turns out to be n log n over 2. This time you actually don't have to touch all coordinates of the hypercube. If you touch all but root n, that's enough to mix. So these are the simplest example, or the classical examples of cutoff. And it's instructive that in both of these and in all the classical examples of cutoff, as the system grows to infinity, also the degree goes to infinity. And this is connected to the scheme of proof. So in the classical examples of cutoff, the lower bound of mixing was obtained by finding a specific event that had that exhibited the lower bound, so that this event A had very different probabilities under the distribution at time t and the station distribution, and that kind of give us a lower bound for the mixing time. The upper bound was obtained by using Cauchy-Schwarz. You bounded L1 by L2. So the L1 distance is essentially twice the total variation. You bound L1 by L2. And then in examples where you understand the spectrum, you can compute the L2 norm of the density. So that was the general scheme. As we'll see, this scheme is very problematic in the case of bounded degree graphs. So in particular, I'll explain why in Ramanujan graphs such a scheme cannot work, because the mixing time in L2 really happens at a different time, a different constant multiple than the mixing time in L1. So the phenomenon of backtracking slows down the mixing in L2 more than it does in L1, and that means that you really need a different idea to prove mixing in L1 in bounded degree graphs. All this will come. So these are the two examples. This is the canonical example of cutoff. You have a hypercube. Half n log n is the mixing time with a lower order correction. Here is the canonical example of non-cutoff, namely a cycle. The mixing time in the cycle is order n squared, but the constant depends on the epsilon that you want. So T mix of epsilon behaves like n squared multiplied by a log of 1 over epsilon. So if you change epsilon, you really change the constant that multiplies the n squared. And so these are kind of contrasting behaviors. And intuitively, cutoff is happening in a high-dimensional situation where mixing involves a lot of different weakly dependent variables that should all somehow reach their stationarity, while in the cases of low dimension, where we really have one variable, then we don't expect cutoff. Now, this is a rough picture, and making it rigorous is one challenge, I guess, posed by Aldos and Diaconis some 30 years ago. Now, we're going to focus from this general setup to the case of random walks and expanders. So a regular expander is a sequence of deregular graphs. It can be defined where this spectral gap is bounded below, or the relaxation time, which is just 1 over the spectral gap, is bounded above. And it also has, of course, a definition, a more combinatorial definition in terms of expansion. But this one will be the more important for us. Now, it's well known in classical that for such graphs, the mixing time, so T mix of epsilon, for any epsilon, if n is large enough, it can be bounded above and below by constant multiples of log n. So the dependence on epsilon is bounded, but the question is, are the C and C prime the same? And, well, not always. So here is, but we'll come to that. Now, we want to understand random walk and expanders. One class of expanders which is better understood are the random regular graphs. And there was an early result by Berstitsky and Duret that says that on G and D, I'm focusing on D equals 3 just for clarity, but everything here works for higher degree as well. So on G and 3, the way the distance from the starting point behaves is very simple. It increases at rate 1/3 until you reach distance log 2n, which is the diameter, and then it stays fixed. So this is the graph of the expected distance. Notice the distance itself fluctuates, but the expected distance to first order has this very simple behavior. Now, where does the 1/3 come from? That's very, very simple to understand, because if you have a 3-regular graph, it is locally like a 3-regular, looks like a 3-regular tree. And on a 3 regular tree, you have a drift of 1/3. With probability 2/3, you move further from the starting point, 1/3 you move closer. So that speed 1/3 is what leads to the factor of 1/3 in this formula and to the 3 in this graph. For general D, 1/3 is going to be replaced by D minus 2 over D, because in a general D regular tree, you have drift of probability D minus 1 over D of going further and 1 over D of going closer to the starting point. So based on this picture, Duret conjectured that the mixing time is asymptotic to 3 log base 2n with high probability. And indeed, this result gives you a lower bound. It cannot mix, or it's actually very easy to get a lower bound of this nature. So the non-trivial aspect is the upper bound. This was proved by Lubetsky and Sly in 2010, that the simple random walk indeed has cutoff at this time. So D over D minus 2 is the speed term, and this multiplies log of n to base D minus 1. And this was based on a reduction of simple random walk to non-backtracking walk, and then a very precise result for the non-backtracking walk. So if you have...
What is the window?
So what is the window? I didn't spell that out. So if we look at T mix of epsilon, and so take epsilon, which is less than half, and look at T mix epsilon, compare it to T mix of 1 minus epsilon. So when epsilon is smaller, this is going to be bigger. And so we say that Wn is a window for the mixing if we have such an inequality holding. So remember, this T mix, let me put an n here. So we have a system of size n. We want this to be bounded by C epsilon times some window size. And to have cutoff, this window should be negligible compared to the mixing time itself. Okay, so cutoff just means that this difference is little o of the mixing time, but sometimes we can get a concrete bound which is better than that, and that is called the window, well, an upper bound for the window. But here, really the best window you can obtain is root log n. So it's not true. So this kind of inequality is true with Wn, which is root log n, but it fails if Wn is little o of root log n. So that's the window, and it reflects in this picture. If we look at the total variation to stationarity, so it decays like that, and the window tells you, right, this is the size of the window where you go from total variation distance 1 minus epsilon to total variation distance epsilon within this window. And of course, the width of the window is influenced by epsilon, but only in this multiplicative constant. Okay. So the way simple random walk is related to the non-backtracking random walk is just by this factor of d over d minus 2. Namely, if you can get a bound for the non-backtracking walk of the mixing time, then you can just multiply that by this factor and get a bound for the simple random walk in L1. This doesn't work in L2, but it works in L1. And the reason is very simple. You can just lift to the tree, and if you look on the tree, a non-backtracking walk is just walking forward on the tree. So if I'm walking for L steps on the tree on a non-backtracking walk, I just reach to a uniform vertex at distance L. But if I do a simple random walk for T steps, then I will still reach a random level of the tree, but this random level is going to be very concentrated near d minus 2 over d times the time. So if I run for time t simple random walk, this will be like running L, which is d minus 2 over d times t. steps of the non-backtracking random walk with a lower order correction, which doesn't matter here because what you'll get is some mixture of levels of the tree, and all these levels will be close to this level with an error of order root t. So this kind of, so maybe I'll write this plus an error of order root t, and this root t will lead to this window of root log n here, because the t that we will need to run will be order log n. So putting these together gives this result for the random deregular graph. On the other hand, okay, I'll skip this and just say that, so this answers for random deregular graph. It turns out that you don't have mixing, you don't have cutoff for all deregular expanders. So characterizing which deregular expanders have cutoff is still a challenge. Let me switch to now to focus on the Ramanujan graphs. Okay, and so I already told you what's a deregular expander, and an important starting point here is the Alon-Bopana theorem that says that if we are now looking not at the eigenvalues of the walk, but the eigenvalues of the adjacency matrix, so this is the different scaling, we don't divide by d. So now we're looking at the adjacency matrix of the graph. The largest eigenvalue is d, and we're looking at the second eigenvalue of this adjacency matrix. And so the Alon-Bopana theorem says that the second eigenvalue is always at least 2 root d minus 2, 2 root d minus 1, minus an error that goes to 0. The significance of this number can be understood in several ways. In particular, it is the spectral radius for the infinite adjacency matrix corresponding to the infinite deregular tree. So with this in mind, Lubotsky-Phillips-Sarnak defined the Ramanujan graph to be a connected deregular graph where all the eigenvalues except plus minus d have magnitude at most 2 root d minus 1. So we're allowing, or they are allowing an eigenvalue of minus d, which corresponds to the bipartite case, as well as d, which is always there, but no other eigenvalues outside this interval. And the motivation for this definition was, well, that they could produce such examples. So Lubotsky-Phillips-Sarnak and separately Margulis in '88 constructed such deregular graphs if d minus 1 is prime. And there is quite recently an existing proofs of such graphs by Marcus Pillman Srivastava for all d. D is at least 3 to have some interesting object. So here is the Lubotsky-Phillips-Sarnak 6 regular Ramanujan graph, or some attempt to view it, when n is, so this is a graph on 12,000 vertices, and so you see that locally around the node it behaves like a tree, up to some point, but of course it's a finite graph, so eventually it stops being a tree, and our goal is to understand the structure over here. Here's another attempt to view, some of this graph. These are the spectral measures of 2 Ramanujan graphs. One is the graph you just saw, and that is in the foreground here. So this gives you the different eigenvalues with the multiplicities. And in the background, you see another graph, which is a random lift of the Peterson graph. It's also a Ramanujan graph in this case, although it's open. So when you take a 3 regular the standard Peterson graph, you do 1,000 lift of that. And some people here know what are random lifts. Otherwise, it's just it's not crucial for me right now. And that's another Ramanujan graph. And the point is to show that the spectral measures of these graphs could vary quite a bit. Right. So I guess it's conjectured that the n lift of a 3 regular graph is Ramanujan with positive probability, but this is, in the picture, you just see a particular sample of this 1000 lift, which is Ramanujan, but there's no, it's open to show that this recipe gives you Ramanujan graphs. Okay, so there are some motivations for looking at expanders. So this was at these Ramanujan graphs specifically, and these were intensively investigated in the 80s and early 90s, but recently there's been renewed interest because of some connections with quantum computing and new insights and questions about distances in these graphs. I can't go into these, but you can find on Peter Sarnak's webpage more information about that. In particular, his student Sardari has shown an infinite family of regular Ramanujan graphs with diameter at least 4/3 times log Pn. I'll come back to how this fits into the general picture. So again, we're going to talk about mixing time, and this is again for the third time recalling these definitions of cutoff. Now, for simple random walk on deregular graphs, there was a conjecture of Noga-Alon that says almost every random deregular graph should be at least weakly Ramanujan, which means that lambda 2 should be 2 root d minus 1 plus a lower order corrections. And this was proved by Friedman in 2008. One conjecture I actually made in 2004 is that all transitive expander sequences should have cutoff. At the time, we didn't have, of course, a counterexample to that, or I wouldn't make the conjecture, but we also didn't have any example. So now at least we have an example. We can show this holds for any family of transitive expanders, which is Ramanujan. However, Eyal and Allen did construct examples of expanders, these are not transitive, that don't have cutoff. So just being an expander sequence is not enough. So here, this relates to what I mentioned earlier. It's the distance of simple random walk from equilibrium. So here you see it on the Lubotsky-Phillips-Sarnak graph. And this is distance in L1 and distance, so distance in L1 is in blue, and distance in L2 capped by 1, so minimum with 1, is in red. And the point to take away from these pictures is both of these seem to have cutoff, and indeed asymptotically we know there is cutoff, but the cutoffs happen at different times. So the ratio between these is not going to 1, and indeed we can prove this rigorously, that cutoff happens in both models. In L2 it actually follows from an old result of Laurent-Soloff-Coste that you must have cutoff, but we know exactly where it happens, and it happens at a strictly later time. So this means that you cannot use directly L2 techniques to prove cutoff on for L1, which we care about on the Ramanujan graphs. However, so if you look at non-backtracking walk, so this is just the walk where you take a step, and then the next step is uniform among all edges except the edge that you just walked on. So if you use non-backtracking walk, then you see from this empirical picture that the mixing in L1 and L2 for the non-backtracking walk happen actually at quite close times. And indeed, asymptotically, I don't have a graph here because asymptotically, as n tends to infinity, non-backtracking walk in L1 and L2 both, just mixes at this number, log is d minus 1 of n to first order. So the constant here is 1, is the point I'm emphasizing. This is for non-backtracking walk. So this is what we want to capitalize on. And here is so let me state the main theorem for the Ramanujan case. So in any sequence of deregular graphs, which is Ramanujan here, I want to make them non-bipartite, but a tiny correction deals with the bipartite case as well. So if they're non-bipartite, then you have cutoff. So the mixing time, T mix epsilon, is d over d minus 2 times log d minus 1n with a lower order correction for all epsilon. Okay, so this is exactly what gives you cutoff. Now, in the bipartite case, of course, the random walk formally never mixes, but you can fix that by making one lazy step. So this is Jonathan here. So this is connected to a general phenomenon conjectured by Aldous and that I've worked out with Jonathan, but I can't but in this case we can just see it directly. So that's Jonathan Hermon. So there's some general phenomenon, but in this case it's very concrete. We can take one lazy step, so with probability half move, with probability half stay in place, and then the rest just run the random walk, and then the result still holds in the bipartite case, exactly the same way. You just have to add a single lazy step. Any question about the statement? Okay. One thing I want to mention, this theorem holds the way I stated it also for weakly Ramanujan graph. You don't need lambda 2 to be strictly less than 2 root d minus 1, and error little o of 1 is fine. And in particular, this reproduces in a much harder way the older result of Allen and Eyal on mixing of random deregular graph, but of course it holds for other graphs beyond the random deregular case, in particular for random lifts. And one can also allow to have a few exceptions. So if the number of exceptions is subpolynomial, namely eigenvalues that are outside the Ramanujan interval, then it's still fine, and you get the same result. One geometric corollary of the results is that it's something about distances in Ramanujan graphs. So we still don't know what is the diameter, or what are the possible diameters of Ramanujan graphs. There's certainly at least log n to base d minus 1, because that's true for any deregular graph. And a result going back to the 80s, proved by Fan Chang and others, is that twice log d minus 1n is an upper bound. So the diameter is between log n to base d minus 1 and twice that. But whether the factor 2 can be attained, we don't know. And that's an open question. One thing we can say is that for most vertices, the true answer is log to base d minus 1n. So if you don't, so the diameter of course concerns the worst case, the furthest pair of vertices. But if I fix x and I ask for vertices y, almost all of them will be a distance log d minus 1n. So those that violate that by even a tiny epsilon will be a little o of n proportion. However, there could be those little o of n proportion which even double this log d minus 1n. So this result easily allows you to recover the fact that the diameter is at most twice log d minus 1n, because if you have any two arbitrary vertices, x and z, you can just use triangle inequality with a random vertex in the middle, and you'll get the upper bound of 2. So it reproduces the known upper bound on diameter, but it tells you that for most vertices the answer is log d minus 1n. And this result, which we obtained from the non-backtracking walk, was proved independently using a different approach by Sardari, who used Chebyshev polynomials. With non-backtracking walks, which is our approach, we can get some more information, because we don't get just distance between vertices, we get distance between directed edges. So if you have fixed the one directed edge, then for almost every other directed edge, you can find a path from the first to the second, a directed path of the requisite length, log d minus 1n. And having a directed path from one edge to another is stronger than just going from a vertex to a vertex, because it's very hard in these graphs to turn around because they tend to have high girth. Okay. We also can demonstrate with cutoff in LP distance. Due to the time, I'm going to not discuss that at length, but we can understand exactly how the mixing time depends on P when you look at the LP distance. And the key takeaway is that it really varies with the different P. So every P that you are looking at gives you a different mixing time. And this is quite different than the picture, say, in the hypercube. The other thing we know is that for all P, the Ramanujan graphs really are the fastest possible mixing of any deregular graph in LP. So for any P, you'll get a different optimal mixing time, and the Ramanujan graphs will saturate that optimum simultaneously for all P. So the key tool, as I've been relating, is this non-backtracking random walks. So that you move from X to an edge. So this is an edge-valued chain. You move from an edge XY to an edge YZ, so that Z not equal X. This has been used as it's quite a popular tool. It was used in Friedman's work and co-authors. It was used by Charles Bordenave in a refinement of this classic work, and in the earlier work of A. Allen I mentioned, and it's also now being used a lot in community detection problems that many people here have worked on. And in our proof on the Ramanujan graphs, we use non-backtracking walks and also some new property of them that I want to highlight. So let A be an adjacency matrix of the graph itself, G, and these lambda 1, lambda 2, and so on are the eigenvalues of the adjacency matrix. We look at a set of directed edges, and then we have this non-backtracking matrix. So B of two edges, u, v, and xy, is going to be just 1 if v equals x, but u must be different from y. So this is exactly the condition that these edges follow each other. And there is a known connection between the eigenvalues of A and of B, known as the Bass formula, that says for any eigenvalue lambda of A, solve this quadratic equation, you get two solutions, and these give you eigenvalues of B, and these give all the interesting eigenvalues of B. There are a few other less interesting ones I'll mention, but these are all the important eigenvalues of B, solutions of this quadratic equation. So this is known, but we can say more. So we can give the exact Jordan decomposition of the non-backtracking matrix. The issue with this non-backtracking matrix, if we want to understand simple random walk, it's classical that we want to diagonalize the matrix and then take powers of this matrix, we understand the simple random walk. The problem with the non-backtracking matrix, it's not diagonalizable, it's not even normal. So it looks like that approach is doomed. And one thing, I mean, this Bass formula is well known, and initially we thought in the Ramanujan case, we shouldn't profit from passing to non-backtracking walks because we have an equivalence between the eigenvalues. And we know that the spectral approach, direct spectral approach to compute L2 distance fails on these graphs of bounded degree. And then, so how could an equivalent form of the spectrum in the non-backtracking case help? But it turns out that it does help. Really, the cause of the difference between L1 and L2 for bounded degree graphs is the backtracking. And once you get rid of the backtracking, you get rid of the difference. So anyway, so what is the result? You have eigenvalues. So if we look at this matrix B, of course, it's much larger than A because it's an edge, it's on the space of edges. So capital N is the number of edges. And so we have a lot of plus minus 1 eigenvalues that are unimportant. There is the eigenvalue d minus 1, which just comes from the fact that the chain from every edge, you have d minus 1 edges you can go to. But then all the interesting eigenvalues happen here in pairs. So these are the Bass eigenvalues you see here. But what we can add to this picture from Bass is that the Jordan form just consists of these small 2x2 cells. And we can say exactly what is the extra term in these cells. Now, this would be straightforward if all the eigenvalues of A were distinct. Because then you have these, for each eigenvalue you solve the quadratic equation, you get a pair, and you have to have this 2x2 structure. The difficulty is that in many cases of interest, in particular the Lubowski-Phillips-Sarnak case, the eigenvalues come with very high multiplicity. And so it's not obvious that you don't get large blocks in the Jordan form, but in fact you don't. They're all 2x2, and we can identify what is this extra term. So in the Ramanujan case, all these extra terms have magnitude exactly d minus 2. Once you have this explicit structure, you can almost work with this as if it's a diagonal matrix and just calculate the behavior of the random walk by taking powers of this matrix, because we really know how to take a power of a 2x2 triangular matrix. That's something we can manage. So just following that, so the idea is, suppose first the matrix was diagonal, and mu t is the distribution of the non-backtracking walk. Then to find the mu t is just obtained by taking b to a high power and normalizing by d minus 1 to the t, because remember, b is not normalized. And then when you do that, you compute the L2 distance. So this would be, if it was diagonal, you would just simply compute this using the eigenvalues. These are the unimportant plus minus 1 eigenvalues. The t we're going to take is log d minus 1n, and this immediately implies that this term will be negligible. And so the term of interest is here, arising from these Bass eigenvalues. And what you get, because we take t to be log d minus 1n, what you'll get here will be easy to compute. So one thing I skipped this slide. So one thing which is known, when you solve this quadratic equation, in the Ramanujan case, all these thetas, all the Bass eigenvalues you get, will lie on a circle of radius root d minus 1. And of course, they come in conjugate pairs. So the main point is they're all of magnitude root d minus 1. So this will be root d minus 1 to the power 2 log n. So this will give you an root d. Oops. Sorry. Getting it wrong. Okay. So this and you have n terms here. So what you get is that this will cancel one factor of the d minus 1 to the t, and what you're left with is, well, essentially n from the number of summons divided by d minus 1 to the t, and by just pushing t a little bigger than log d minus 1n, you will make this smaller than epsilon. This would be the picture if the matrix is diagonal. It's not diagonal, but it's close enough that the same argument works with a small correction. And so instead of a constant here, we need to go a log n, but then the argument goes through. So the last thing I want to say about this before briefly returning to the random graphs is to mention one tool that we use. So this is a tool from this book with Russ Lyons, Probability on Trees and Networks, which was finally a couple of months ago submitted to the publisher after 19 years. But it's still available, will stay freely available on the web. Anyway, so this is the tool. If you have B as a non-backtracking matrix, B inverse is its inverse. B is invertible. And if you take B inverse and add D minus 1 times B inverse to B, then miraculously the matrix you get, it's now a matrix on the edge set, it's symmetric. And you can write out explicitly what it is and check that it's symmetric. The point is that this, of course, we started with the matrix A, which is itself symmetric, the JCD matrix of the original graph, but that's a smaller space. C is a matrix on the same space, the edge space, as B, and it's symmetric, so we know it is diagonalizable. But when you have this form, it's easy to go back and forth between eigenvalues of B and eigenvalues of C, because if you have any eigenvalue of B, then you take that eigenvalue and add D minus 1 times its inverse, you'll get an eigenvalue of C. But because C is symmetric, it is diagonalizable, and this is one explanation of the simple structure of this Jordan form. Questions about this? Okay, so now I want to just quickly turn to tell you what are the substantial differences in the random case. So in the Erdős-Renyi random graph model, you have the different phases, and we'll be focusing on the supercritical phase and random walk on the giant cluster. I'll have to skip this picture. The random walk on the critical, inside the critical window is very interesting, but now we're going to focus on the supercritical case where, so P is larger than 1 over n, so 1 plus epsilon over n, say, but here epsilon is fixed, not going to 0. And then the size of the component is some constant times n. The mixing time is log squared of n. And this was discovered by Reid Funtoulakis and independently slightly later by Benjamin Kozmer-Wormald. And why is this mixing time log squared of n? It's easy to understand the lower bound because the structure of the giant component is that it has these long paths that connect to the main body of length log n. If you start at the end of this long path, it will take you time at least log squared n to reach the main body, so that gives you a lower bound for the mixing time. And then the non-trivial thing is to show that after you reach the main body, it's still only log squared n, so you also have an upper bound. Let me say that even if you look at the 2-core, so you remove all the leaves and keep removing the leaves, you still get log squared n because there are long paths here that are in the 2-core, and if you start in the middle of such a path, you'll still have log squared n. So the mixing time is order log squared n, and there's no cutoff because the mixing time is dominated by random walk on a path, and there's no cutoff there. It could take an arbitrarily large constant times log squared n. So what we find in this case is you get a more interesting behavior when you start from a typical vertex as opposed to from this worst case. And I'll just maybe jump to what is the result. And the result is that the mixing time here is order log n. And there is cutoff when you start at a uniform vertex. So this is quenched. So you choose a vertex uniformly at random, and then you fix that vertex and look at the mixing time from that vertex. And it's log n times some known constants from the behavior of random walks on Galton-Watson trees. And I can't go into much detail on these constants, but I'll say that this constant here, v, represents the speed of random walk on the Galton-Watson tree. So just like in this case, the speed of random walk on the regular tree played a role. Here in the random graph, the local structure is not of a regular tree, but of a branching process, a Galton-Watson tree, and the speed of random walk on that comes in. But we also have another factor, which is if you have a regular tree, then obviously random walk will spread uniformly on every level when it hits that level. This is no longer true on Galton-Watson trees. Namely, there you have some non-uniformity of the hitting distribution. If you look at the level k and wait till the random walk hits level k, it doesn't hit it uniformly. It hits it in a highly non-uniform way. And in fact, if the size of the kth level is some mean to the k, there will be a strictly smaller set of size, say mean minus delta to the k, which supports the random walk. And this is the dimension of harmonic measure, which comes in these mixing estimates. So, so I have to skip many details and just end with a couple of open problems. So one which is open, but we've recently made progress, again with Eyal and also Anna Ben Hamu, is the case of comparing non-backtracking walk to simple random walk. So here I should really mention something about non-backtracking walk in this random setting. So we talked about it in the Ramanujan case, but one can also look at non-backtracking walk in the random case. It's easier to analyze in the random case than the simple random walk, and it basically can be analyzed by an adaptation of the proof from the regular graphs case. So the non-backtracking random walk, you also have a cutoff, and this part for non-backtracking walk was in our paper, but also independently in work of Anna Ben Hamu and Justine Salez, who is here somewhere. Justine? Oh, there, thanks. And he will talk about related work later. What? And right, and they have more information on the window in this case. So looking at these two things prompts a question: does non-backtracking walk mix faster in the random graph with given degree sequence, say, than simple random walk? So here I don't want to look at Erdős-Renyi graph because that has leaves. So let's take a random graph with a random degree sequence with no leaves. So all degrees are at least 2. So the non-backtracking walk is well defined. Is it true that the non-backtracking walk mixes faster? So that we still don't know, but what we recently with Anna Ben Hamu and Eyal verified that it's true if all degrees are strictly bigger than 2. So, yes?
You're saying that I have a random graph and I condition that the mean degree is at least 3, right?
So I have, it's not, so I fix the degree sequence. All the degrees are, that's right, so in our theorem, all the degrees are at least 3. And now pick a uniform graph among all graphs with this degree sequence and compare the mixing time of the simple random walk and the non-backtracking walk. Now, of course, backtracking is wasteful, so it's natural to expect that the non-backtracking walk will mix faster. The difficulty is that this waste in the random case, this waste also leads to the simple random walk is also more selective on where it goes. So it doesn't enter very thin parts of the graph, it tends to backtrack more out of them. So we have a tension between two factors. On the one hand, canceling the backtracking speeds you up. On the other hand, canceling the backtracking also makes the walk less selective, and you have to see how the tension between these two factors. So that creates some complications, but we can handle them if degrees are bigger than 2. And finally, returning more to the regular case, one thing that is still open is this original conjecture: does lazy simple random walk have cutoff on every family of transitive deregular expanders? We now know it in the Ramanujan case, but I still believe it's true in greater generality. Thanks for your attention.